Good evening, all of you. Today we'll be starting the session shortly. We'll wait for 2 minutes, 2 or 3 minutes, then we'll start. I think it's time. Today we will be discussing about the topics which we studied in this week 10 of the course of PAM Practical Applications, Design, Simulation and Implementation. Uh, Before going to week 10, we did in what we did in week 8 and week 9. So basically we'll just go through that. So in week 8 we went through these like designing a thermocouple for that, and how we designed that control systems and controllers, different controllers which we use for that. And then we also looked about ECG, signal acquisition circuit, and we tried to acquire this beats per minute, which is also QRX complex. Then we saw that how these filters can be used, to remove that power line interference, uh, artifacts based and monitoring all these noises using LPF designing, high pass filter designing, notch filters, etc. Then we also use half wave rectifier. Then then we use a threshold circuit, basically a peak detector circuit, and then we gave it to that final op amp so that we can get the beats per minute. So so these were the things which we studied till now. So in today's lecture, we will be talking about analog multipliers, what are they, how they are implemented using op amps, and we also did some experiments over that. And then we'll also look into like automatic gain controllers, then ADC, analog to digital converters, and then we'll look into DACs also, digital. A DAC will be looking in the next week, but yeah, we will look into ADCs more today in this week. So if we start with basics of analog multipliers, so just change this. Okay, so yeah, so basics of analog multiplier. So basically, what is an analog multiplier? It's a device which multiplies two signal, which we can say Vx or we can say X in more generalized term, X and Y, and giving output V out, which is XY, by divided by some scaling factor k. So this is like we say this is a scale factor, and this can have the dimension of voltage if we are talking about, if we are like giving the input sets voltages. 1 minute. Okay. Yeah. So the dimension of this voltage. If the inputs are, if the inputs are in voltage form. Okay. So this is the thing. So then this can be Vx, Vy by k. Now, in analog multipliers, simply we see that these are some uh, uh, these basically divide two input, they multiply two input signals, and we get the output as this one. Okay. Then these are of three types. That is single quadrant. Then there is two quadrant. Then there is we can say four quadrants. Okay. Yeah, and this four quadrants and all these things like Vx, Vi, Vy, and Vout. So in single quadrant, this is only single polarity. So this is unipolar. This is also unipolar, and we get output also as unipolar, having only one polarity. After that, uh, we have then two quadrant, that is one input is bipolar, another is unipolar. So the output will be what? Bipolar. But in case of four quadrants, this is what we actually want. This is the ideal behavior which we want from analog multipliers, because whether the signals are having negative or positive polarity, like it should not matter. It should not matter to that analog multiplier. It should like multiply both of the signals, and accordingly it should give the output. So four quadrant system, the Vx is bipolar, Vy is also bipolar, and Vout is resultant is bipolar. So this is there. So this is about analog multipliers. So there are logarithmic multipliers also, as the name suggests. Logarithmic multipliers. Okay, as the name suggests, we use two log functions. This is one log, another log. Then we add them, and we get an anti-log. That is, so here it is x signal. This is y. So basically, log operation is happening. That is like log of x. If we add both log of y in this point, then what we'll get, this is basically log xy. If we take anti-log, so we'll get this one. Okay, so this is logarithmic multipliers. In this also, like we can have logarithmic like divider also, logarithmic division. So in this case, instead of adder we have subtraction. This is subtracted. Based on that, we again take anti-log, and we get x by y. So till here what is happening? That is log of x minus log of y, which is log of x by y. So we are taking anti-log and we are getting this. Okay. Now we talk about these quadrants with these type of analog multipliers. So uh, we have a concept of Gilbert cell in this. Gilbert cell. So Gilbert cell is basically using transistors, getting this getting output as the multiplication of the input signals. So in this cell, we have basically a voltage divider circuit at the input side of one of the transistor. We have one collector current, this another IC2. We have another transistor, and they are connected. They are emitter junctions. This is another resistor, and we have another input from this side, that is Vy. Okay, this is Vx input, that is Vy input. We have 10 ohms, and this is 10 kilo ohm resistor. So in this case, so if we talk about the relation between the collector current of a silicon junction transistor and tran conductance, so these are related as TIC by dVB equals to QIC KT. So where K is Boltzmann constant, T is the temperature, IC is the collector current, Q is the charge. So this is the main equation. Using this, Gilbert was able to make this analog multiplier. So what he did, the IC1 minus IC2, that is change in IC, delta IC, equals to Q by KT, that is the constant. IC is given by Vy plus VB is the diode, this base to emitter junction diode reverse potential, reverse bias voltage, divided by the resistance 4.7 into 10. So we get the IC here, and it be this VB, it will be 10 upon 100. Okay, so this equation he got. Now after further giving the values of Boltzmann constant, charge and temperature, we were able to get 8.3 into 10 to the power minus 6 constant plus Vy plus 0.6 for silicon diode into Vx. So this was at 25 degrees Celsius. So we were able to achieve the multiplication of the input signals, but here there was some limitation. The limitations were that, first of all, this is only a single quadrant, so we cannot like we cannot achieve a four quadrant analog multiplier from this case. And another thing, we were having disadvantages if we talk about. So disadvantages were that, like so the Y input was having is offset by VBE, and that is non-linear. So this is non-linear VB. It changes. We have the characteristics of VB, so it changes. So that's why this is non-linear thing. Another problem was the Vx input is also non-linear. Okay, so and scale factor includes temperature term. includes temperature T in it. So as we saw here, this one. So these were the factors which were limiting the working of this Gilbert cell. But then again, there was some modification in this itself. So he proposed like he tried to multiply currents rather than the voltages and tried to like get the analog multiplier circuit. So for that, he first realized a dual quadrant multiplier. So in this case, he used two transistors. Okay, and then so these were the two input currents, I delta Ix minus delta Ix. These were the collector currents, IC1, IC2, Q1, Q2. This was diode D1, D2. This is ID1, ID2. Okay, this is Iy by alpha. So here, like the output relation which we got from this thing was delta IC, change in the collector current, was change in Iy divided by Ix. So this was linear in function, linear in nature, and so yeah, so this he was able to achieve, but still this was dual quadrant. So in order to achieve like the full quadrant system from this full quadrant, or we can say uh, four quadrant, like four quadrant cell from this, we can use the pairs of these transistors together. So that can be given by again the same thing. We have two transistors together in a pair, then we have another transistor. Okay, so here again we have another set of pair for transistors. So here was the one input IL2, here was another output, sorry, the current output IL2, IL1. This is IL1. This we can take as IC3. This was IC4, Q3, Q4, Q5, Q6, Q2, Q1. We have IC1 collector current here, IC2 collector current here, and then we were getting this plus this is V1 voltage, first input voltage, and the second input voltage was, sorry, was given by this was plus, and this was V2, V1, V2. Okay, this is IEE. So using this just for the knowledge, like if we talk about the IC3 current, it will be IC1 1 plus e to the power minus V1 by Vt. Similarly, IC4 will be IC1. So this is the fourth quadrant. the emitter current, that is IC1 in this case for IC3, IC4 also, IC1 is the emitter current. So it will be IC1 divided by 1 plus E V1 by Vt. Okay. Similarly for this pair, this is IC5, this is IC6. IC5 can be given as the emitter current, that is IC2, this one. Okay. Then divide by 1 plus e to the power the voltage V1 by Vt. This is the voltage C. Uh, this is the voltage negative of negative. It will be positive in this case. So this is negative voltage of V1 going to the Q5, and for this Q6, yeah, Q6 is connected from here like this. Okay, so here it will be IC6 equals to IC2 emitter current 1 plus e to the minus V1 by Vt. Okay, now for Q1 and Q2 transistors, Q1 and Q2 transistors, we get IC1, the collector current is IEE, that is the emitter current, divided by 1 plus the voltage, then IC2 equals to IEE 1 plus e to the power V2 by Vt. Okay, so this is the case. Now if we substitute these two equations in the above equations, then finally we will get del I, what is the differential output current. Differential output current is del of I equals to IL1 minus IL2. These are the output currents, which is equals to, we can write them as IC3 by IC5 minus IC4 plus IC6. So by rearranging and substituting, we finally get delta I equals to IEE tan of H divided by V1 to Vt tan of H V2 by 2Vt. So by further calculations and further if we assume some things, then we can able to achieve the V1 and V2 multiplication. But here also there is hyperbolic function, but still we are able to get this multiplication of V1 and V2 in the final equation of delta I. So that is there. Okay, so this was about Gilbert cells. Now we can also use multipliers with op amps. Now we saw that how analog multipliers can be are achieved, and we can, now we can use these for arithmetic, using op amps for different arithmetic operations. So that is division operation if we talk about. So if we have a op amp configuration like this, and we have our registers here, we have a analog multiplier here, we are feeding back this output voltage to this analog multiplier, and we have a signal V2. So V1 is this. So how will in this case what will be the output? Output will be if we say this current and this current are same, so, and the output here it is V2 V0 by K. K is the scaling factor of this. Yeah. So yeah, I'm talking about the multipliers with op amps. So in this, for this arithmetic operations, so we have an analog multiplier in the feedback of this op amp, and then to get the output voltage, the output of this analog multiplier is V2 V naught by K. So since these two currents are same, so we can equate them and we can get V1 by R equals to minus V2 V naught by KR. Based on that, we can get V naught equals to minus V1 K by V2. Okay, one for another application of this op amp is if we use op amps like V naught and we have a multiplier here, then we have we are multiplying again a V2 signal here. So V naught is being fed back to this op amp, and here it is V naught. So we get at the output of this analog multiplier is V naught V2 by K. So since these two voltages should be equal, so V1 equals to V naught V2 by K because of virtual short. V naught V2, yeah. So V naught will be V1 K by. So this was inverting configuration for using multipliers to get this division operation, and this is the non-inverting configuration. Okay, yeah, after that like we did one experiment also using analog multipliers with that development board. So in that development board we were having analog multipliers in that, and we were using two analog multipliers. One we didn't use, that is for like uh, correcting the offset and like giving the negative feedback to the op amp. We can use that this last one op amp, but we didn't use there. So basically we used these two op amps, then we had a multiplier core here, and it was being fed to this op amp. Okay, like this, and the output of this op amp is given by x1 minus x2, y1 minus y2. If you are not using z1, then this is divided by the scaling factor SF. So this was x1 x2, this was y1 y2, this was z1 z2. Now yeah, this was there. Then yeah, so then we gave x1 as 5 sine omega t, and x2 as DC voltage 3.3 volts, and then we checked, like, sorry, y1 as, and x2 was 0, and even y2 was also 0. So we then checked the output, and we were getting the multiplication of 5 sine omega t into 3.3 divided by the scaling factor. So this was this was in the experiments. Then we also learned about this automatic gain controllers. So in this automatic gain controller, as the name suggests, it will control the gain of the basically it will maintain the output constant, or the output of the op amp as a constant term. So it has characteristics like this. So this is the threshold voltage, which we can say VPI. After this, if we increase the if this input voltage is increased, then there will be no fluctuations in the output, and this output is given by 2 V reference. Okay, so this was there. So we had a circuit also where, first we were inputting our input signal. Yeah. So we were inputting our input signal. Then we had a squarer, that is like it will multiply with its own unit, and we were then using a reference voltage Vref here, Here there was a amp with a negative feedback, and this was grounded, and this was being fed back here. Okay, and there was an integrator to detect the peak and maintain the constant output as constant voltage. So this was the configuration for this automatic gain controller. Then here also, yeah. So like by intuition we can say that if the output is directly proportional to the input and VC by A, VC is the basically the uh, the feedback, the voltage feedback to the signal. So if V in is increasing, then VC will decrease to maintain V naught constant. It will be vice versa. If VC is increasing, then V in will be decreasing. So this is how like automatic gain controller was working. Then we came. Hello. Yes.
Sir, in assignment 10, first
Hello.
question is the analog multiplier output should retain in four
Wait.
quadrant.
Your voice is not audible. Wait. Am my voice audible to you?
Yeah, your voice is audible, sir.
Wait. Wait. I think your voice is coming in. Okay. I think your voice is coming in the desktop. I don't know why. Uh, yeah. Tell me. Yeah. Tell me. Hello.
Sir, am I audible?
Yeah. 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 Tell me. Tell me.
Okay. Sir, in assignment 10, first question,
Okay.
the
Okay.
analog multiplier output should retain in four quadrant one ideally. So that means analog multiplier can be in any of the quadrants, no, sir? It
Yeah.
need not be in fourth quadrant, no, sir?
No, no. Actually, four quadrant is basically the like the optimum that what we say, the requirement from an analog multiplier. If it is four quadrant, then it can work like with any signal. If the signal is having positive polarity or negative, or even positive itself, so then it can work in every way possible. So that's what
Yeah,
we actually required. Yeah.
yeah, I thought that it can be in any of the quadrant, either quadrant 1 or quadrant 2, 3 or 4.
Oh, okay.
So
Nah.
that is why I thought that it is wrong, sir.
Oh, no, no, it is saying that it is four quadrant. That means it can work in any like it is not
See,
single or dual, it's four quadrant.
sir, ideally, why it has to be 4 quadrant? It can be in any quadrant, no, sir?
Actually, ideally, because that's what I'm saying. If you give Vx and Vy signal, then what happens like see if Vx is only limited to the positive polarity, that is unipolar. Okay, so then we cannot achieve the all the functionalities from this multiplier now. If you have a signal which is in let's say negative polarity signal, so you cannot give to that multiplier. But if it is in four quadrant, you can use any signal in that.
Okay, sir, okay.
So yeah. So I will discuss first this assignment question itself. I will revise that. I think yeah.
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 Yes, sir. Thank you, sir.
Okay. Okay. So then yeah, I think I will go with this assignment questions first initially.
Okay.
So yeah. So week 10 assignment question 1, as which of the following statements are true? The analog multiplier output should retain in four quadrant one ideally. So they are saying that the statement is saying it should be ideally as a it should behave as a four quadrant analog multiplier, and like four quadrant you can have plus minus polarity for Vx, and for Vy also plus minus polarity. So you can like give all the signals to that analog multiplier. The multiplier can work in every way possible. Okay, so that is there. So another thing, huh. Anil, are you able to hear my voice?
Yes, sir. Yes, sir. I am able to hear, sir.
Okay, but I'm not able to. hear your voice in my earphones. I don't know why. I will check.
Am I audible, sir?
Yeah, you are audible, but from my desktop, this. Now, can you speak something?
Yes, sir. Yes, sir.
Now it is fine. Okay. Yeah, yeah. So yeah,
Okay, sir.
yeah. Thank you. So yeah, week 10 assignment. The first question is, yeah, as I discussed that. So we need ideally a four quadrant system. So it can we
Sir,
can get.
now is not, sir. Now your voice is not as clear as earlier.
Oh, is it? Uh,
Now it is okay, sir.
Now is it fine?
Now it is fine, sir. Now it is.
Okay. Just let me know when it is not fine. Okay. Yeah.
Okay, sir. Yes.
So now, so first this so yeah we are talking about this first question. Then four quadrant. Ideally, we want a four quadrant system because we can give then any value of polarity, any value of voltage polarity into that system. Next question is next statement is log anti-log amplifiers are single quadrant operation. So this also this is a factual fact-based question. You can easily based on the seeing the lectures you can answer this first question itself. Okay. Now the second question, that is if you have any doubts you can ask me. Otherwise I will go through all the questions like all the anyway I will be going through all the questions. Okay.
Okay, sir.
Yeah, yeah. Now the second question is design an analog multiplier to give an unsaturated output. So they are saying they need unsaturated output if the operating voltage of the circuit is provided with plus minus 15 volts. So we are giving a supply of plus minus 15 volt and internal reference voltage Vref is set to 10 volts. Okay. Compute the conditions for Vx and Vy. So the let Vx and Vy are the inputs to the analog multiplier. So we have Vx Vy by V reference equals to V output. So normally V reference is the scaling factor. If nothing is given, then we take that V reference as the scaling factor this for this analog multiplier. So we have this V reference is 10 and what will be Vx and Vy so that it should be less than 15 volts. Okay. Now the thing is if we see in the if we see the like the options. So if we see the first option, then they are saying Vx and Vy should be greater than 10 volt.
Sir, is
Yeah.
this is the only way going from the options or anything like?
Or you can say, okay, let's say if not from options, you just see that okay, Vx Vy by 10 is less than 15 volts we need. Okay,
Yes, sir.
but we don't have any absolute values there. So okay, let's say if we have then yeah, I think then you will have to compare with the options itself
Okay. Okay.
because I think that will be easy for you because we don't
Okay.
have any other data apart from this reference voltage and the supply voltage. So in
Okay.
that way, or you can say one more thing like Vx Vy should be less than 150 volts. Okay. So
Okay.
i- just to satisfy this condition, you will have to go with these options. Like if we talk about the first option, then it is like greater than 10 and 10. So if it is let's say 15 and 15, then it will it will not fit into this condition. So this cannot be there. If we so anyway
Sir,
Vx and yeah.
suppose Vx is greater than 10, Vy is greater than 10. Suppose 10.5, 10.5.
But but that is there till what say like 10.5 it will work. Then 11 also I think it will work. 11 into 11, 12 into
Yeah.
12 also work. But
Yeah.
still this is the open end, na, the other side. It is greater than 10 volt. So it can be anything beyond 10. It can be 20 also. That will not satisfy. So we will that's why we'll have to limit the condition because this is the open end.
Okay, sir. Okay.
Getting my point? It can be
Yes,
anything
sir.
beyond 10. So that's why it is there. So that's why based on that you can answer this question then, like which option will be the correct option. Okay. So this is done. Then next question. What is the minimum number of comparators needed for a 10-bit flash type ADC? This is also very easy. 2 to the power n minus 1 is the uh, this is like easy. Then fourth question, let the current flowing through the circuit is measured using a. So I think last class some people have doubt in this. I also watched these. I think week 12. Somebody was saying that these questions are referred from week 11 lectures, but I didn't find. But still, I think it just getting like simply from the intuition you can answer these questions. If you answer the first question, then you can answer the rest of the questions also. So let's say we'll try how we can solve this question. So first is, let the current flowing through the circuit is measured using 0.1 ohm shunt resistor. Okay, the voltage drop across the resistor is, so we have a zero point 0.1 ohm resistor, and so whatever the voltage drop, whatever the current will be flowing, so it will be, the voltage will be what, IR. So it will be according, it will be directly proportional to the current through the circuit, linearly proportional to the current through the circuit, if we go like this. Then if we have this, then fifth question, the next question, what it's saying, in continuation to the previous problem, let the current through the circuit is to be represented using a voltage display module in which 1 volt input is represented as 1.00. So we have
Excuse me, sir.
yes.
Sir, in question for may I think it's simply like Ohm's law.
Yeah, Ohm's law. Ohm's law. But in previous class, like we all were thinking like whether is it referring to some part of the lecture or not. So that's what we were in the previous class, we were confused. But now, yeah, I think with the basic thing also, you can say it is like linearly proportional to the current. Hmm.
Because from the question we cannot say it is belonging to which one.
Yeah, yeah. So yeah, it is straightforward. Fourth one.
Okay, sir.
Okay. Then the fifth question. So fifth question is saying we have to represent something like this on the display module. So suggest a suitable method to represent the current reading used to display. So now we have a resistor from which a current is flowing. It is a zero point 0.1 ohm. So we have some voltage drop. So that is 0.1 I. So now in order to uh, so now I think, yeah, if we talk about now the options, the drop across the resistor measured using an instrumentation amplifier having a gain of 1 can directly be connected to the module for representing the current. Okay, the drop across the resistor measured using an INA of gain zero point 0.1 can directly be connected to the module for representing the current. I think zero point 0.1 this will not work because anyway already we have a less signal 0.1 I. Already we have a factor of zero point 0.1. We cannot attenuate this further. Okay, and if we need 1 volt here, that means uh, represented using a voltage display model in which 1 volt input is represented as 1 volt. So we basically we need a 1 volt here. So if we have a gain of 1, so it will be zero point 0.1 I into 1, it will be zero point 0.1 I itself. So this also we cannot use. So if we have a gain of 10, then this factor will be 1.1 into 10 I, which will be I. So if we have a 1 ampere current, then we can get a 1 voltage here at the output. Okay, so like the most suitable option I am finding this here as C. Then the next question, in continuation to problem 4, okay, this fourth problem, let the output drop across the resistor is acquired using a 3-bit ADC having a reference voltage 5 volts. So they are saying V reference is 5 volts. Okay, if the maximum current through the circuit is 1 ampere, maximum current through the circuit is 1 ampere. Okay, here they are mentioning maximum
Sir,
current 1 ampere. Yes.
here there is no information regarding what type of ADC.
Okay, so
So by
so
default we used to.
No, you have to go with the basic concept of ODC, ADC. So
Okay.
I see only the functioning of the ADC is different, but the output and the way it takes the input and the output, I think they are same only. They convert the digital form, they take the analog input. So that is constant in every ADC. So
Okay.
accordingly we have to see, okay, which of the, so okay, I will tell you the process, then you will be able to
Okay.
know, okay, we don't
Okay.
require the type of ADC here. I will give you one question. I have some extra questions today. So there, like if you want to find the what we say, the the conversion time, or the time taken by the ADC to convert from analog to digital, then you will be requiring this type of ADC is required. But in this case, I think it will not be required. We'll see. Okay.
Okay.
Yeah.
Okay.
So if the maximum current, so the current 1 ampere, so compute the level of ADC, the input signal will match. So okay, so this is 5 volts. The resistor is required using a 3-bit ADC having a reference voltage. If the maximum current through this, compute the level of ADC, the input signal will match. Okay, so we are basically attaching our ADC here. Then we are measuring this. So now we have 1 ampere maximum current going from this is zero point 0.1 ohm, so we'll get what, zero point 0.1 volt here. Then if we have zero point 0.1 volt with the level, so yeah, so now we'll check the resolution of the ADC. So what is that? It is the V full scale divided by 2 to the power n. So it will be 2, and we have number of bits of the ADC, that is 8. See, 8 it is, and V full scale
Sir,
is, yeah.
why in the denominator we have taken 2 power n? Why not it is 2 power n minus 1?
So actually, that I also like thought like why it is there. So there is IEEE standard, like IEEE standard, but I will just write it here. So we take resolution of range divided by 2 to the power n. This is decided by the IEEE standards 1241. You can check the standard. Okay. So
Okay, sir.
they decide this, that they will be taking this, but sometimes they take this also, range of 2 to the power n minus 1. So these are used for the integrated circuits. So this is normally for commercial devices, which are devices already in like market, commercial devices.
So by default, I should take the first one, sir.
First one you take. Okay. Don't take this one. So these are for integrated circuits. So but you take this one, range divided by 2 to the power n. Okay. So now we have this one. So VFS is what, that is the 5 volt divided by 8. So we will get something 0.625. So this point volt is very less than 0.625. So means like it is even less than the minimum value which ADC can quantify. So that's why we will have like zero level for this answer question.
Sir,
Okay.
is the number of levels 8 is fixed or can I have less than that?
It is fixed because we have
It is
3-bit ADC.
okay.
If we
Because
have
my reference voltage is 5 volts.
huh.
Can I have number of levels less than 8?
No, see, it's not like see, if you are having less reference voltage also, then the levels will be same only 8, but the voltages will be then different. Or yeah, then you can have, let's say, okay, you are saying this now. So okay, I will do one thing. We have a 5 reference voltage, but we now have what,
5 levels.
5 levels. No, if we have 3 bit of ADC,
Yeah.
then what will have?
Wi-
Hmm.
With 3 bit, I can have maximum 8 levels, sir.
Hmm.
So can I have 5 levels less than 8?
Oh, that you don't have, that you can't have, cannot have, because it should be in the power of, in the this 2 to the power n factor, na.
Okay, can I have four levels, sir?
Yeah, 4 you can have from n equals to 2 bit. If you are having
Okay.
2 bit of my ADC, then you can have 4 levels.
No, no, sir. For 3-bit ADC, can I have four levels? That's what.
3 bit, see, it can go for 3 bit, you can like you can get up to 4 levels, that is not an issue. But
Uh,
inherently it will be having 8. Getting my point?
in, no,
See,
sir, no. Inherently, it will be 8. I did not get.
see, okay, wait. So we have, let's say n equals to 3 bit. So based on that, let's say we will go with this question only. So we have a 5 volt reference voltage and we have resolution that is 0.625. So if we talk
Okay.
about the reference, if we talk about the levels here, it will be 0.625, then 0.625 into 2, 0.625 into 3, till 0.625 into what we say, uh, first will be, yeah, 0 na, zeroth level, then first level, second, third, fourth, 5, 6, 7th. So this will be into 7. So if our reference voltage, like so if it is limited by this one, like the supply voltage, or let's say we are not able to give the enough supply. So first of all we'll see what is 0.625 into 7. So what is this, 43. Okay, so this is 4.365 volts. So we have a reference voltage of 5 volts. So it can achieve 7 levels only. But if we had, let's say, yeah, it can achieve this one. So you're getting my point. So you can have, like, you can have till 4 levels also. That is not an issue. But these levels will be there existing. So if you get a signal which is more than the fourth level, then you will be getting that level.
Okay. So if I choose four levels, anything greater than fourth level, it will be automatically taken as 5.
See, in 3 bit you cannot limit your that system as a 4 levels.
Okay.
But
So,
so if in yeah, getting my point.
so 3-bit means 8 levels, 4-bit means 16 levels. That is fixed, sir.
Yeah, yeah, fixed. That is fixed.
Okay. So that means all the time I used to take the best resolution only.
It see, it is good to have good, like, nowadays there are like normally which we use, like I use in my research, I use a 14-bit ADC.
Okay.
Okay, so see, this much of levels, 2 to the power 14, we can have this much of quantization levels. So that makes our signal more nicely looking. So you can have as many as number of bits so that you can increase your resolution. But at the same time, you will have to bear with the cost and all those things. So for high bit ADCs, you will have to pay more. That is the thing. Since the circuit will be complex.
Yeah, yes, sir. That is why if I have a
Hmm.
choice of reducing number of levels, my cost will get reduced.
Yeah, cost will
Of
reduce,
course.
but you will not have that much of accuracy in your signal. Your
Yes,
signal
sir.
will
Yes.
not be precise. Okay,
Okay.
that is there is a trade-off, so you can like balance these things in between. Okay.
Okay. Okay.
So yeah, so this question I think uh, clear. Okay, so we'll move to
Okay.
the next question. In the next question, it is saying, in continuation to the previous problem, this previous problem 6 question, select your approach for representing the current through the circuit with a resolution of 125 milliampere without changing the resolution of ADC. So they are saying they don't have to change the resolution of ADC. So how they can do that? So if they have a 125 milliampere current going from zero point 0.1 ohm resistor, so this will be what, 12.5 volts millivolts. So if we see the options, if we see this option, amplify the voltage drop, if we see 12.5 multiplied by 50, we will get 0.625 volts. So this is the minimum value which like this can be uh, the resolution, this is equal to the resolution of the ADC, so we can use this option, like if we amplify the voltage drop by 50, gain of 50. Okay.
Sir, earlier reference voltage by number of levels, that is what is resolution we told.
Mm-hmm.
Now 125 milliamperes.
Now, so they are saying that now if they see, so now this is the minimum. See, there is a resolution. So we have a circuit like this. Okay, there is a current. So this is also a system, na? Here we are giving some current. So they are saying for this system, how much minimum value of current we can give. That is resolution. That is the minimum value of current. So they are saying
Here
if
IE is
we
125 milliamperes,
ha,
sir.
so this is, yeah, I is the minimum value of current which we can give to this system. So at the same time they are saying, so what thing we should attach here? Okay, what should be here at this point, so that our ADC, without changing the resolution of the ADC, it can measure the minimum value of the current, that is 125 milliampere. That is what the question is saying. Got it?
Okay, sir. Okay.
Hmm. So this is the thing.
In fact, I did not get an idea that there is a resistor in front of ADC. That is the problem.
See, actually you can simply think like that. uh, I'll just clear this thing. uh, there was some system, there was some resistor output from that system, then you need to use some circuit, you don't know what you will be using, so that your ADC can read. So this is basically a part of existing system. Okay, maybe you are reading some you are reading, let's say it's an anything, like it's an ammeter something. Okay, from
Okay,
which I
okay,
is outputted, and you have a shunt resistor 0.1 ohm.
okay, sir.
So
Okay,
this system you were having. So and you were having this ADC also, but you have to interface both of these things. So what thing you will be adding in between to interface them correctly? Okay, so
okay,
that's why these things are there. Hmm. So this is the seventh question. Now the eighth question. In continuation to the previous problem, compute the level of ADC when the input current is zero point 0.5 ampere. So same previous problem. Compute the level of ADC when the input is current is zero point 0.5 ampere. So zero point 0.5 into what? Uh, zero point 0.5 into zero point 0.1, that is 0.05. But then we have a gain of 50. So we have 2.5 volts. So you can check 2.5 volt is on which level, like 0 to 4 or 8. So that is based on the resolution, so 0.625. Similarly, you can go to first level, second level, third level, like this, and you can get where you are getting the 2.5 voltage. So you can answer this also. Okay, I think this is also okay. This eighth question.
yeah, okay, sir.
Okay, na? Yeah. So ninth question. A 0 to 10 volt sine wave signal is connected to an ADC which has a reference voltage of, so we have a ADC which can go from like plus minus 10 volts. So plus 10 to minus 10 volts. Select your approach to maximize the use of resolution. So here they are saying like, but we have a signal which is 0 to 10 volt. Now if we see the options, let's say if we go with this option, then what will happen? So if we increase the gain of this, so what it will do, it will make the signal from 0 to 20 volts, but our ADC can read only till 10 volts. So it will be an issue for this ADC, okay, to read this signal 0 to 20 volts. Now if we attenuate a signal, anyway attenuation is not good because uh, we lost some information. So if we attenuate, this will be 0 to 5 volt.
Sir, sorry, sir. Can you repeat?
Which starting,
No, no, 0 to 20 volts. His input is going to 0 to 20 volts, sir.
yeah, because if we use an input signal with a gain of 2, amplifying the input
Oh,
signal.
from the options. Okay,
Ha
okay.
ha. Okay,
Okay, sir. Okay, sir.
so that is there. So it will be 0 to 20 volts. So that is not acceptable with this ADC having only plus 10 volt maximum. Okay, so then uh, if we go with the second option, then second option anyway attenuating is not a good practice to do. It will anyway some information may be lost, or if we are having a very less signal which is near to, let's say, 0 to 1 volt, in between that in millivolts, attenuating it by 2, it itself will make that signal prone to many noises, and we will not be able to get this output faithfully. Okay, then we are left with this thing by varying the reference voltage of ADC to 0 to 10 volts. So yeah, so if we can change the reference voltage of ADC, then if it is between 0 to 10 volts, then signals can be read easily. Okay.
Will there be any other way, sir?
uh, See
I mean,
first.
apart from the options.
mm, I think you can directly measure also, like giving simply the 0 to 10 to this ADC. It can measure, it will measure, it is having because this. But then yeah, but then I think this is the best way you can do, because only you have to change the bias voltage, like the supply voltage. That is easy to do. Instead of changing the whole ADC, you only simply have to change the supply voltage, that reference voltage.
Okay.
Got it? Hmm. So this is there. Then the last question, a flash. Uh,
Sir, that means the resolution is changing, na, sir? In ninth question. Resolution is changing with a minus 10
uh,
reference voltage and plus 10 reference voltage.
yeah,
Resolution is
yeah,
changing.
yeah. It is changing. It is changing.
But we want the maximum resolution.
Maximize the use of resolution. So see, in this case, it will be 10 by 2 to the power whatever the n will be. But in this case, it was 20 by 2 to the power n. So here resolution high. Here it is less.
Okay.
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 Yeah. So this question is also okay. Then we have a flash ADC is. This is very simple question. You can answer this. So this is factual based question. Okay. So this was about week 10 assignment questions. So I have some extra questions, simple questions only. So yeah, so we'll go with the first question. For a 12-bit ADC with voltage in 0 to 5 volt, what is the resolution? So I think you can answer this question. So range is what? V full scale divided by 2 to the power n, which is 5 minus V max minus V minimum, that is 5 minus 0, 2 to the power 12. Oh, okay. How much you will get? Wait, I have the answer. So it will be 1.22 millivolt. Okay. So just read this question. I'll have some water. What is? Okay, leave it. Yeah. Question 2 is 10-bit ADC has a full scale of this one, 10.230 volts. When the digital output is this one, that is the full scale output of a 10 bit. So we have 10 bits here, 1 2 3 4 5 6 7 8 9 10. Okay, now they are saying what is the quantization error. uh, so quantization error basically in lectures also you must have observed that it is one half of LSB, plus minus half of LSB. So what is LSB? Least significant bit reading, that is resolution of the ADC. So this is resolution of the ADC. So what it will be? So VFS divided by 2 to the power. This is basically a gate question. 2 to the power 10. Okay. So this will be, we have full scale value 10.230 divided by 2 to the power 10. So we'll get what? We'll get I think, yeah, 10 millivolts, approx 10 millivolts. Okay, and then the quantization error will be what? Quantization error will be half of resolution, or the half of LSP, that is 5 millivolts. Okay, this was the question.
Sir,
Hmm.
sir, actually, I think I missed out this quantization error as plus or minus half LSB during the lecture or something.
In lecture
How,
it was, wait, it was,
maybe I missed out, I think, sir, but how do we get that, sir?
uh, that is like, there is no, uh, we simply like quantify this quantization error as half of LSP. So I think when I will just, I'm seeing where he taught this thing. Wait. Huh. When he was telling about the effect of quantization, na? So you see the lectures effect of quantization. So in when we were saying when we are quantizing things, so so he also talked about quantization error, like it is the it is what it is difference between the signals value and the associated binary value. So what we are getting from the binary value and what was the actual signal. So if you remember, he showed that quantization error. This is a like half LSP. This is minus half LSP. This is 0. So it is also like a random noise, like it will be like this. It will be like this random noise. Okay. So this is normally the graph for this quantization error. So this was the concept, and for that he told that it is plus minus half LSP, that like the quantization error. Okay, so this was
Sir,
hmm.
sorry, sir, I did not get it.
Yeah, I think it just I think if you'll go again through the lecture now, you will get only
No,
this much he mentioned this thing.
yeah, yeah. Plus or minus half LSB. LSB is the resolution, that is okay.
Hmm.
But how do we come to know that quantization error is half LSB? You have drawn a waveform which is representing noise and it is varying in between minus half to plus half LSB.
Acha, you are saying how we get this formula?
Yes, sir, yes, sir.
Oh, that that even I'll also have to look.
Okay. Okay.
Yeah,
Because
there may be some, yeah, there may be some statistical reason why we got this exactly half LSP. Uh,
if it is to
okay.
be taken granted, okay, sir. No problem.
No, no, I will tell you in this next class. Okay,
Okay,
next class
okay.
why we took half LSP. Okay, so see, in this section in this course, like these are just the what we'll say, just the introduction to what is sampling, quantification, coding. This full dedicated study in that which you do, like because in one of next question, like let's say this one SNR. So SNR, that is signal to noise ratio. For that, like so first of all, read the question. Worst case SNR of a 10-bit ADC is, although he hasn't teach you about SNR, but you should be aware of what is SNR. So for SNR value is given for any ADC is 6.02 number of bits plus 1.76 dB. So this is the formula for any SNR of for the SNR of any DB any ADC. Okay, for ADC, that is signal
For
to noise
any,
ratio.
irrespective of type of ADC, sir.
Irrespective of type of ADC. Okay, so
Okay.
this is the thing. So now how this now again the question, if how this arise this thing, then there may be some derivation which we'll have to look. Similarly as how that half LSP arised, that we'll have to do.
Okay, sir.
I'll clear in that next class. So if we solve this question, so they are saying the resolution is increased by 2 bits. So they already had a SNR of 57 dB for 10 bit ADC. Okay. So now it is increased to 2, increased by 2 bits. So what will be a SNR for 2 bits extra? It will be, if we say n is number of bits, that is 2 bits increased. So this will be yeah. So this will be what? This will be around 13.8 dB. Okay. So now this much of SNR will be added to 57 dB. 57 plus 13.8. So total SNR of this will become 17.8 dB. Got it?
Okay, sir. Okay, sir.
So increasing the number of bits, as you were saying, can be, yeah. So yeah. So we are like increasing the SNR also. So basically,
Sir,
signal to noise ratio is what? Signal divided by noise. If it is good, if it is good, like it is high, then we have very good signal. We are achieving very good signal. Noise is very less in that.
okay, sir.
Okay, so if we are increasing the number of bits, that means we are less prone to noise. Okay,
Okay.
so now we were at the, so yeah, this is done. Yeah, which of the following is true in case of sampling frequency in ADC? I think you can answer. Just read the question and options.
Small doubt, sir.
Hmm?
Sir, if we divide 10.23 divided by 2 power 10, then answer will be like 0.22. So, that any.
This one.
Yes, sir.
Oh, okay. I didn't calculate. Yeah, I. Yeah. What is the answer?
10.23 divided by 2 power 10 is equal to around star 10. Okay,
How much?
sir. 9.9
Ah,
milli. Okay. Okay, sir.
yeah.
Then
All
around
close.
10,
है ना?
10 millivolts. Okay.
Yeah. So the people who have joined just now, if they have any assignment question doubts till week 10, they can ask me. Okay. Anyway, I'm like answering. I'm solving some extra questions. So yeah. So we were on this sampling frequency. This one. Which of the following is true in case of sampling frequency in ADC? So sampling frequency should be less than highest frequency in signal. So they are first signal. First question. This is Fs should be less than F max. One thing, sampling frequency should be equal to F max. Sampling frequency should be low as possible. Okay, very less, or we can say sorry, approximately zero. What this option is, sampling frequency should be at least twice the that of high, 2 F max. So I think based on the lectures, this should be the right answer because we need sampling frequency so that it becomes two times of the maximum so that we can faithfully get the signal. And there was one more criteria, since this is the criteria, but when you use systems practically, just go with Fs greater than 10 times of Fmax. That's with that at least 10 times of Fmax, so that will help you in generating your signal more faithfully. Instead of this, go with this. Okay, so this is also okay. Then yeah, for 10-bit digital RAM PTC using 500 kilohertz, the maximum conversion time is. So for the reference, these are the conversion times. So from this also you can see, as this is not given in the class, but this is important also. Like we have four types of ADCs: flash, dual slope.
Sir, do we get questions similar to like this in
Yeah,
our exams?
just for the knowledge I have given. If he hasn't taught anything, something like this, you will not get.
Okay, sir.
If he will give, he will also give the like some reference like this, so you can answer accordingly. Okay.
Okay, sir.
Yeah, but don't worry. If it is not being taught, then you will not get that. But
So
anyway,
we can
this,
strict,
yeah,
we,
yeah,
we can strictly follow the lectures that are being given.
yeah. That is like required in each and every course which you study. Just follow that. Just apply your mind in at the time of exam to solve
Okay.
the what we say little difficult questions. That's all. You will be able to
Okay.
solve. है ना?
Okay. Okay.
So yeah. So this is for question 4 is just for the knowledge purpose. Like we mentioned about, okay, in that sigma delta was there, but here it is not. So here like anyway we taught about SAR flash dual slope. So see so for flash it is the fastest, this because it takes only one clock cycle irrespective of the input, is irrespective of the number of comparators and all, because all are parallel. So this is the fastest. Then if we have SAR, irrespective of the yeah, based on the number of bits it takes, like according to that the number of clock cycles are there, and time is NTCLK. TCLK the clock, the time period of the clock pulse which is given to this. Then we'll not talk about this, we have not read this. Then dual slope, it is the slowest. This one is the slowest, okay, because it is having this much of large time, but it is the accurate of all. This is the accurate of all. Hmm. So now if we come back to the question, for 10-bit digital ramp ATC using 500 kilohertz, the maximum conversion time. So they are saying digital ramp is always ramp signal is our we dual slope signal, okay, because in dual slope we have something like this, ramps. So there so if we use this equation, then it will be, so total time it will be, conversion time is 2 to the n plus 1 TCLK, which will be 10 plus 1, this will be 1 by 500 kilo. So you will get the answer. Okay, now the I think no doubt in this question. Next question, the advantage using a dual slope ADC in a digital voltmeter is that I just told you, but again uh, it requires a comparator, so this cannot be there. It gives output, no such thing is there. Its conversion time is small, nah, its accuracy is, its conversion time is very high. So its accuracy high, that's why we use dual slope ATC. Okay, so this question you can expect, I think. Yeah. Which of the following types of ADC is also known as continuous conversion time ADC? So continuous conversion time, it is successive approximation ADC, because continuously it is like converting the signal, like whatever it is getting. Either it is so you must have seen like this. So if a signal is more than this 8 volts, then it will go up. So it will be like what we say, one wait, what was that? Yeah, it will be like then 0 1 0 0. If it is less than this, then it will go like this, 0 1 1 0 0 0 1 0, and so on. Similarly like at this, at the bottom of that. So continuously it is like solving whatever the input you are giving, so it is converting it into the digital domain. Okay. So this is also there. So now among the following four, the slowest ADC is, so slowest, as I told you, the integrating type ADC, because with this we know it is having only one clock pulse time, like one count only needed, successive appropriation and number of bits are needed. In this counting type, it is I think 2 to the power n or something. to the n minus 1. Yeah, so this is there, and I just solved this question. Yeah, we have the last question. Read the question. A temperature in the range of minus 40 to 55 degrees Celsius is to be measured with a resolution of 0.1 degrees Celsius. The minimum number of ADC bits required to get a matching dynamic range of temperature sensor is. So it's also very easy. Resolution, we have this formula, uh, T max T min divided by 2 to the power n. Okay, so this will be 55, that is the maximum temperature, minus or minus 40, 2 to the power n. This is 0.1. This will be 95. So if we solve this, then we can get the number of bits. So let's say if you are getting what we say, if you are getting something like let's say 9.4 something, to the power n equals to 9.4. So you should not go for then what we say, lower bit values. Like lower bit will be what, 8 bits. Now you always go with 10 bit value. Then don't round off it to lower values, even if it is not, because I'm talking about n. Wait, this, if n is like this, n is something like this, so then round off will be n equals to 10, and it should not be equal to 8, because we should prefer always a one bit higher than what we are getting. Okay, so this is the thing. Yeah, if it was n equals to 8, then it n equals to 8. No need to go for n equals to 10 or n equals to 9 something. Okay, so these were some extra questions. So yeah, do you have any other doubts till week 10 in any assignment questions?
Sir, week 9, question 5.
Okay, week 9 question 5. Okay, I don't have, I think here I don't have it. Oh, I have, I think I have. Wait. Question 9. Hmm.
Question 5, sir, 5.
Oh, question 5. Huh. Okay. Okay, I will explain it again. Wait. So I will just open it here. So in this question, we are having uh, op amp having this configuration. We have two diodes in this, T1, this is T2, D1, 2 kilo ohms, then we have 1 kilo ohms, we have the input, this is grounded, V0, and the input wave is given by this one. Okay, this is V input plus 1 T by 2 T, this is minus 1 volt. Compute the average output voltage. So we need to compute average output voltage V naught and diode cut in is 0.3 volts. Okay, so now we'll go step by step. So first, so we have we'll talk about positive cycle. So now when we give positive cycle to this op amp, V in is positive, then what will happen? uh, Whenever the diodes are there, just see this what we say, the op amp as a comparator, like this. Simply see that okay, V in is here, we have a ground voltage, we have a diode here, and it is being fed here, and another diode is here, something like this. It is not connected here, just for the moment, just for the starting moment. Then what will happen? If a positive voltage V in is given, so this is 0 voltage, so this is positive, so this is but non inverting terminal, so we will get what? Minus V set. Okay, if we get minus V set, then this diode is receiving a negative voltage from its cathode side, so this will get on forward bias, but this will be off, this D2 diode. So our circuit will look like this: minus plus, we have then cut in voltage 0.3 volts. The D2 diode is off, we don't need to bother about that. This is V in. Okay, now now we have now let's see, simply now we have to just solve what is the output here in this case. So we can get the current, which is what say, V in by 1k. This is going to this 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 branch, so it will be 0 minus 2k V in 1k minus 0.3 equals to V naught. It will be V in is 1 volt, so it will be 2.3 volts minus positive cycle. Okay, then for negative cycle, again think that okay, compare it, it is acting as a comparator, and we have a negative voltage here. So since this is in non-invert, in the inverting side of the op amp, we'll get a plus V set here. So our diode D2, it was like this, connected to this. D1 will get open, it was connected like this, so this will be on, this will be off, so we'll get something like this. It will be, this is V in, we have V naught here, that is what 0.3 volts, this is 1k. So simply then V naught will be what? 0.3 volts. Okay, because we simply use a KVL here, so it will be 0.3 volts. So now we have, so we need V naught average, that will be minus 2.3 into half t by 2 time, for because for t by 2 time we are getting this voltage, because this voltage was still t by 2, plus 0.3 into t by 2 divided by what? T, total time, that is the average voltage for a square wave. Okay, so it will be t cancel, this will be minus 2 divided by minus 1 volt. The answer will be minus 1 volt, V not average. Clear?
Yeah, okay, sir.
Yeah, any other doubts?
Sir, 6 also, sir. Follow.
Okay, the roll-off factor of the filter is, yeah, I think this question, like somebody simulated this question and then they were able to like get okay 20 dB. I tried with transfer function. I also like my transfer function was not able to, like it was becoming complicated, but in the end you can solve this using a transfer function. Okay, so I don't maybe wait whether I'll see if I have the solution or not. So I will just help you like this. So we have some values for this. Let's say this one is uh, C2, this is C1, this is R3, we have V0, this is R2, R1, Vi. So if you simply you will have to get the transfer function by calculating the by using simple nodal equation here. So what I did, like let's say this is the V1 voltage, so V1 minus Vi by R1 first, plus V1 by R2 plus V1 S C1 in this branch, okay, because this is 0 volts. Then we have V1 minus V0 by into SC2 equals to V0. Okay, and we also have one another equation, that is uh, for this, like for this branch, that is minus V1 SC1 minus V0 R3 equals to 0. So V0 sorry, V1 is SC1 R3. So this is equation, let's say 1, this is 2. If we substitute this V1 value in this one, okay, so what I did first, I used a nodal equation here at this point, then I got something like this. Then what I did, like I also utilize the this is basically a negative, what we say, inverting amplifier. So I utilize that equation and use this thing here. So I got this second equation. If we put V1 in terms in this first equation, then we'll get something like this: 1 by R1 plus 1 by R2 plus SC1 plus SC2 minus Vi by R1 V0 S C2. Okay, so then V0 by Vi will be, it will be little bit 1 by R1 SC2 plus 1 by SC1 R3, 1 by R1 plus 1 by R2 plus SC1 plus SC2. So if you solve this question, if you solve this equation, then you can get the roll of factor from this from the characteristics equation. So there will be some characteristic equation, that is the equation at the denominator. So you will get something at numerator and something at in terms of s square or something in the denominator. So that is the characteristic equation. So based on that you can get the roll of factor. But yeah, have you studied these Bode plots or something? Have you studied control systems?
Yeah, studied, sir, but
Okay, okay.
not yet.
So I think then you can get the, like, based on, I think there are some rules, like if you have some let's say type 1 factor, type 2 factor, s square is there something, then you
Yeah.
have a gain like roll of a 40. If you have s only, then you have a like slope of 20, something like that. If you have a factor
Okay.
of square
Okay.
also, है ना? So based
Okay.
on that you can solve this. Yeah, that is there. Any other question?
So regarding examination,
Mm-hmm.
is there any patterns here, like number of questions?
Pattern I don't know actually. That,
Uh,
yeah, I think
so
just like assignment questions you will get maybe, but exactly I don't have any idea how the pattern will be. But just go through the assignment questions. I think go through the lectures. That will be enough.
okay.
Any other doubts? So if you don't have any doubts, then I think we can end this session here.
Okay, sir.
Yeah. Okay. So Farhan and Prashanti, do you have any doubts? Sorry? No. Okay, I think if no doubts are there, then I think we can end this session here. So we'll meet next week. Yeah,
Okay, sir.
yeah, we'll meet next week. I will come with some extra questions so that it will help you in your assignments. Oh, sorry, assignments. I will in your test. So it may help you in test. I don't know, but I'll try my best to get some extra questions. Okay, thank you, Prashanti. Yeah. Okay, then we'll end
Okay.
this session. Yeah.
Okay, sir. Thank you,
Thank
sir.
you.